Hello, everyone. Welcome to the very last talk of the conference, and we left the best talk to the end. So hopefully you are not all too tired. And we have the great honor to host Da-Wei Wang, who will be today talking about topological phases of quantized light. If you have any questions, please put them in the Q&A or in the chat, and that way we'll try to answer them at the end of his talk. Thank you.
Thank you, Maria. And I would like first to thank Stephen and Ming-Chi and Peng Xue for this invitation to give a talk here. And although this is the first time I'm joining this conference, I already found it's a very high profile conference, and it's really a great honor to be here to introduce our recent research on the topological physics of quantized light. And I'm Da-Wei Wang from Zhejiang University. And today I'm going to give you a brief introduction of how the topological idea evolved from mathematics to condensed matter physics in the 80s. And about a little bit more than 10 years ago, it was extended to photonic structures. And our recent research is basically try to apply this mathematical tool to study some new phenomena in the quantized light. So you cannot observe such phenomena in classical optics. And at the end, I'm also going to talk about some experimental realization of this effect. So this is basically the outline of my talk. So first, I'm going to talk about topology and the topological states of electrons, and then give you some brief overview of the topological photonics in photonic crystals, etc. And then I will focus on the topological phases in the quantized Fock-state lattices, in particular the one-dimensional Su-Schriefer-Heeger model and the 2D Lifshitz topological transition, as well as the valley Hall effect and the Holden model. So first, the topology is originally a mathematical concept that describes the properties of a geometric object that are preserved under continuous deformation. So here I give 3 examples. So this Mobius stripe, the property is that it always has one edge, and this cup, which can be continuously deformed into a torus, but it can only contains one hole. That is something that does not change. And this sphere, it can become a cow, but there's no hole in it during this deformation. And the most important theorem in topology of mathematics is the Gauss-Bonnet theorem, which gives the relation between the deformation and what is changing during the deformation and what is not changed. So the Gaussian curvature, which describes the curvature, the local deformation of the surface. If you make integration of this Gaussian curvature over the whole manifold, you will find that is related to the number of holes in this manifold. For example, if you have a sphere, then you make the Gaussian curvature integration, then you are going to find that is 4 pi, which actually everybody knows that is how we calculate the surface of this sphere. And for this torus, if you make the integration, you will find, well, that is the total integration will become 0. And you have one hole in this torus. So it still satisfies this theorem. And if you have 2 hole torus, you are going to get the total integration of the Gaussian curvature to be a minus 4 pi. And in the 80s, there's a very famous physical phenomena found by von Klitzing, which is the quantum Hall effect, which later people found that is closely related to the topological nature of the electron band structure. So first, Klitzing found that if you increase the magnetic field applied to a two-dimensional electron gas and measure the Hall resistance, you will find that is basically you will find at the very large magnetic field, the resistivity is quantized to some plateaus, and is inversely proportional to 1 over n, and n is an integer. This can be explained with the quantized Landau levels. If you have electrons in two-dimensional electrons in a magnetic field, the electrons are going to have cyclotron motion and localized with a certain radius in a plane. But if you have edge, the electrons cannot make this cyclotron motion because it can hit the edge and then have directional currents. And at the two edges, the currents direction are different, opposite actually. And if you have a certain group of electron gas that the field to a certain Fermi level, and if you apply electric field perpendicular to the edge, you are going to have a different Fermi surface at the two edges, such that you have different number of electrons travel in the opposite directions, and this is the Hall current. Von Klitzing basically use a sample that is not so clean, but still he found very robust Hall plateau. So why is the quantum Hall effect so robust against all the defects in the sample? It was found that it's because of the topology of the band structure of the electron gas. And this was found in 1984 by TKNN, the so-called TKNN paper, T for Solis, who won the Nobel Prize a couple years ago. So here I first have a brief introduction of the band structure of electrons in the lattice. So if you have a square lattice and a tight banding model for the electrons, after diagonalization, you will find, well, the Brillouin zone is this the eigenstates of the electrons can be described by those momentum states in this Brillouin zone, and the left side, the left edge and right edge of this Brillouin zone actually are describing the same states. So we can we can rule it to form this cylinder, and the upper side and the downside are actually also describing the same states. So you are going to have this torus structure of the Brillouin zone, and on the quantum Hall effect finally found to be related to some local properties of this in this Brillouin zone of the eigenstates. It's not the energy, but it's defined in a very strange way that people found, well, it can be rewritten in some familiar form if people are that people have encountered in the electromagnetics. So first, with the eigenwave function, we can define something called Barry connection, which is corresponding and very similar to the vector potential of electromagnetics. And with this vector potential, you can define the Barry curvature, make a curve of this Barry connection. And the Hall conductivity actually is proportional to the integration of the Barry curvature of all the field bands. So that must be an integer number. And this is the origin of the quantized Hall effect. So with this, Haldane found that, well, if you have the quantum Hall effect only related to the topology or the band structure, so it's not necessary that you have the Landau levels. So Haldane construct a model which is based on the honeycomb structure, the tight banding honeycomb structure, and he introduced the next nearest neighbor hopping attached with the phase, such that the electrons feel a periodic magnetic field without a net magnetic field, so they cannot form Landau levels. And with this, he found that the band structure, the two bands have different twin numbers, so that there's an edge state between these two bands, which is chiral. So there's a famous correspondence, which is called the bulk edge correspondence. If you have different twin numbers of the band, there's always chiral edge states between these two bands. They can carry the whole quantum Hall states and contribute to the quantum Hall effect. About 20 years later, this model was not realized. So he tried to find some analog in optical materials, in photonic crystals, basically, that if you have a honeycomb photonic crystal, you can also construct an analog of the quantum Hall states, and you can observe these chiral edge states. And this was realized just 1 year later in microwave material, that people observe, well, there are these kind of states that if you excite them, the microwave can only travel in one direction. And if you have obstacle in the to stop this microwave, actually you cannot succeed, because the microwave will go around this obstacle and travel still in the same direction, because there's no backward mode over there. The backward mode is on the other edge, and it's very difficult to scatter the microwave to the other edge. So this is something people think promising to have some applications in the waveguides. And very quickly, this kind of materials has been extended to photonic waveguides, that people also see similar effect with light. And now this is a bigger material that, this is a big area that I cannot cover everything, but as you can see, it has been extended to metamaterials, to silicon photonics, and to some virtual lattice structures like the time, in the time being quantum walk, and as well as in the ring cavities in the synthetic, so-called synthetic dimensions. And people have also did some interesting research in higher dimension, like higher than 3-dimension lattices that people cannot synthesize, people cannot have in the real space lattice. So here I would like to summarize why people can study these kind of topological states of electrons by making analog of the Maxwell equation and the Schrödinger equation. So here I give an example. If you make a paradoxical approximation of the Maxwell equation, for example, in this waveguide structure, you will find the Maxwell equation. If you reduce one of the, in the propagation direction, if you reduce the second derivative to the first derivative with the slowly varying envelope approximation, then the equation is very similar to the Schrödinger equation by making analog of this spatial dimension in the propagation direction with the time t. At the same time, the light spread in these different waveguides describes the kinetic momentum, kinetic energy of the electron, and also the refractive index plays the role of the potential of the electron. So these equations have the similar structures, such that you can use the Maxwell equation to mimic the Schrödinger equation. So basically, all these studies are based on the Maxwell equations, and you can immediately see that you don't need to make the second quantization. That is to say, you can use the classical light rather than any quantum light like single photons to observe all these effects. That is also why people can observe it in many materials and just in normal conditions. And the topology and the quantum are not related over here. The only thing that you need to pay attention is that light is bosonic, it's not fermionic. So you are not going to measure something similar to the quantum Hall effect. Rather, you are going to directly excite those edge states and observe the chiral propagation of those states. That is the way people did the experiments. And people also did some research in the atom light hybrid system. So and it's not only that you in some photonic structure such that the material only play some role of the refractive index, that you can also have atoms that you can quantumly control, such that they can possess some peculiar behavior, you know, and to guide the light to travel also only in one direction. And there's an area called chiral quantum optics that is also a similar thing, that you have a waveguide, you have atoms coupled to these waveguide modes, and they have some chiral properties. This is basically just to select those atom modes and to study the interaction between the atoms and the atom. And previously, we also did some research in the lattice structure that we call super-radius lattices, which is based on the EIT system, that you couple the atoms with the several control field such that you can construct a lattice structure in the momentum space. And you probe this lattice, then you compare the super-radius emission and to study the topological nature of this kind of lattice. So I would like to see that these are semi-classical quantum optics, so that the light you can use in these systems can also just be classical light. And the atoms, the quantum system are the atoms, and they just work as a passive medium for the topological photonics. So it's still, I would say, it's still the topological photonics for classical light. And of course, people also use quantum light sources in the topological photonics. So for example, recently people have developed the idea and the technology of topological insulator lasers that by using some lasing medium in the edge modes, you can make some very special laser that possess very excellent properties of the very good properties of the laser. And you can also integrate some quantum light sources into the topological mode, such that you have entangled photons generated in different topological modes. But again, although you have a topological light over here, the topological modes and the quantum light source are independent. So there's no relation between the quantum and the topology over here. So about 10 years ago, when I was a PhD student of Renbao Liu, during the discussion, he gave me a note that described a very interesting idea, that to synthesize gauge fields in a solid of arbitrary dimension, and he gave an example of the Holden model. So the idea is basically, it's possible that we use just multiple light beams and use the Fock-states in these light beams to construct a lattice structure. And we found that this lattice structure exists in the D-1 dimension if you have D light fields. So, and there's no constraint on the dimensionality. You can have arbitrarily high dimension, actually, and with a very sophisticated design, that you can introduce some lattice structure just similar to the Holden model. And he gave a brief proposal on this. And but later we found that it's really difficult to realize in the experiment, until we later in the collaboration with Mária Scully that we found, well, if you have superradius and in the EIT system, you can construct a lattice structure in the momentum space. And the different sites in this lattice possess different momentums, which actually is the phase correlation of the excited atoms in the medium. And with this, we propose several interesting phenomena that can be observed in quantum optical systems, including the Holden model. And very recently, we also observed these chiral edge currents in room temperature atoms, which was only possible in ultra-cooled atoms if you use their momentum degree of freedom. But however, all these studies based on the superradius lattice are still semi-classical, that we use classical light to construct some topological model. And the quantization of the light field is absent. Until recently, I had a collaboration with my colleague, Da-Wei Wang, and he has a very interesting and a very advanced experimental platform on the superconducting circuits. And we synthesize the antisymmetric interaction and observe the chiral behavior of the excitations in these qubits. And then we found, well, probably we can use this structure to simulate some ideas we had years ago. So here, let me first introduce what are the phenomena that people can only observe with quantized light. Actually, it turns out not many of them. The early examples includes the black body radiation, the lamp shift, and the actually against many people's knowledge, the photoelectric effect actually can be explained with the classical light. And later, a very famous example that you need to use quantized light is the GC model, that when an electromagnetic field or a cavity field is coupled with an atom, so first the light can only be in some Fock states that possess the integer number of photons. Then if you consider both the degree of freedom of the atom and the light, you are going to have these kind of states in the Hilbert space, that the atom light states are coupled pairwise. So if you have the atom in the ground state, and at the same time you have one photon in the cavity, the photon can be absorbed by the atom, of course, and then you have 0 photon in the cavity and the atom in the excited state. And the coupling strength is the vacuum Rabi splitting. And if you have 2 photons in the cavity, and you are going to have square root of 2 coupling strength. And the coupling strength is proportional to the square root of number of photons in the cavity. This comes from the property of the annihilation operator, that you apply the annihilation operator to a photon number n states, you are going to have square root of n, and then the n-1 photon number states. And this was observed more than 20 years ago in cavity QED system, that you have a cavity field which is in the covariant states. Then you couple the a single 2-level atom to this field, you are going to observe the Rabi oscillation. So if you have classical field, which I mean, if you consider, well, it's just there's no such quantization of the light field, you are going to have very perfect Rabi oscillation from 0 to 1 of the 2-level atom. However, if you couple the light field to the atom, you are going to observe that the Rabi oscillation will gradually become smaller and smaller due to the interference between the Rabi oscillation in different subspaces. And if you make a Fourier transform of this Rabi oscillation, you are going to find frequencies proportional to the square root of n. So, and this has become a standard method to make field, to make tomography of the quantum states of the cavity. So here, I just want to make a very small extension of this model, which is the multimode GC model. Let's consider if the qubit is coupled not only to one cavity, but many cavities. For example, here we have 3 cavities, and the coupling strength between the atom and the cavities depends on how many photons are there in the cavities. For example, if you have 1 photon, then the coupling strength is square root of 2. So that means the photon that can be observed by the cavity, the strength of the photon to be absorbed by the cavity is enhanced by the square root of the photon numbers in the cavity plus 1. So this is basically due to the social behavior of bosons. They like to stay together. If you have many numbers of photons in one cavity, then the atom prefer very much to emit another photon into this cavity rather than to the other cavities. So we have this computation between the cavities to obtain 1 photon from the qubit, and you are going to have a whole Hilbert space of this very complicated computation for many cavity fields. And in the next slides, I'm going to give a brief overview of the structure. So here we have a Hamiltonian, and we have D cavities coupled to the 2-level atom. This Hamiltonian conserves the excitation numbers, of course. So if you sum together all the photons in the cavity and the atom excitation, they give you a conserved number. And here I just note a simplified notation that a circle means the atom on the ground state, and these are 3 numbers, or 1 number or 2 number or 3 numbers, they just denote the photon numbers in different cavities, and the square denote the atom in the excited state. So if you have, I have this table to show in different dimension, in different D, the number of cavities with different total number excitations, you are going to have different structures. For example, for D equals to 1, which is the normal GC model, just the atom coupled to a single cavity, then you are going to have just 2 states coupled together. If the atom on the ground state is coupled to, and you have just 1 photon in the cavity, is coupled to the atom in the excited state, and you have 0 photon in the cavity. And if you have 2 photons, then it can only couple to the 1 photon in the cavity and the atom on the excited state, and the same thing here. So that is just another representation of the interaction we have introduced just a couple of slides ago. But the coupling strength is different. So here you have square root of 1, here you have square root of 2, and here you have square root of 3. I use different thickness of the line connecting these 2 states to describe this difference in the coupling strength. And if you have 2 cavities, then the thing becomes a little bit more complicated, because if you have 1 photon, the photon can be in the first cavity, it can also be in the second cavity, but they all couple to the atom on the excited state and no photon in the cavity state. So you have these 3 states coupled together. Basically we can read it from the left side to the right side. So first the atom in the ground state and the first cavity have 1 photon, and this photon can be absorbed by the atom, and there's no photon in the cavity. This atom can emit a photon in the second cavity, and then you have this state. So these 3 states connect together. And if you have 2 photons, you are going to have a longer line. So 2 photons in the first cavity, no photon in the second cavity, then couple to the states, then move to the right side, you are going to have all the photons in the second cavity. And if you have three cavities, it's longer. So all these states are going to form a one-dimensional lattice. And if you have three cavities, just like the previous slice, the three photons can be in, you have one photon, in the one photon case, you have the photon can stay in either of the three cavities, then you have these four states form this structure of this Hamiltonian. And then if you have two photons, you are going to have this structure. And if you have three photons, it's a little bit more complicated, but you can see that it's going to grow to a graphene structure, a honeycomb structure. Basically, it has two sublattices, and you have edges because the photon number can only reduce to 0. It cannot be negative numbers, so you must have an edge of this lattice. And for if you have four cavities, of course, the structure is going to become three-dimensional. And you can actually continue this calculation to d equal to 5, which corresponds to four-dimensional structure, and study the physics over there. But here we only focus on the d equals to 2 and d equal to 3 case. So before I introduce the 1D Fock-state lattice, I would like to first see a little bit about the Su-Schriefer-Heeger model, which is a tight banding lattice that plays a very important role in topological physics. So if you have a bipartite tight banding lattice that you have two different coupling strengths, one is V, the other is W, describing the connection, the hopping coefficients within one unit cell and between different unit cells. And there's a topological number which people call also the Whiting number that you can calculate from the eigenstates of this model, that depending on the relative strength of V and W, this number will be 0 or 1. So when V is bigger than W, which means the coupling strength within the unit cell is larger than the one between the unit cells, you are going to have a 0 Whiting number. And all the states, they can, in a limit that W equal to 0, that they form this dimerized structure. And if in the other limit, V is smaller than W, the Whiting number equals to 1, and you are going to have edge states in this in this phase. That is because well, the edge is the edge between a non-trivial Whiting number and the vacuum. So there must be these edge states. And for the general case that just a V smaller than W, the edge states does not just locate on the edge side, but they have some extend. They have some tail into the bulk, but still, you know, they still localize to one of the edges. So this is a very simple model, but it shows the essence of the topology, how topology plays with this one-dimensional lattice. So here, let's come back to the two-mode GC model that I just draw a little bit longer Fock-state lattices that contain 15 photons. So it also contains two kinds of lattice site corresponding to the atom in the ground states and the atom in the excited state. And from left to right, you can see that the cavity photon, photons in the cavity, in the first cavity is gradually decreasing, while the photon number in the second cavity is increasing. And we need to remember that the coupling strength between neighboring sites is proportional to the photon number in the corresponding cavities. So here I define T1 as the coupling strength due to the first cavity, and T2 is the coupling strength due to the second cavity. And they are going to have different values. For example, here on the very left side, T1 is proportional to square root of 15, while T2 is 1. So T1 is much larger than T2. While on the other side, so T1 is 1 and T2 is square root of 15. So their relative strength is inversed. And at the middle of the lattice, they are relatively, at the middle of the lattice, there's a site that they equal to each other. So according to the calculation in the previous slides, there's going to be an edge state over here. And this is also the model that the states that Su-Schriefer already discussed in their original paper. There must be an edge state, which they call a soliton state, at the edge of this lattice, and they only occupy one of the lattice, one of the sublattices, and their energy is 0. And here, yes, we have this state. You just calculate this GC model and make a diagonalization. You are going to find a 0 energy state, and this state locate at the boundary of these two phases. I mean, when the photon number in the two cavities are relatively similar to each other, and it has 0 energy. It only occupy one of the lattices, which means only occupy the lattice side when the atom in the ground state. And the reason actually is also very easy. So you have two cavities coupled to the atom. We can make a combination of these two cavities to form a bright mode. So A1 and A2 coupled to the atom. So we just make A1 plus A2 to be a bright mode. And the A1 minus A2 then become a dark mode, which is decoupled from the cavity. So in the A1 and A2 mode, we are going to have this kind of lattice structure. But in this B1, the bright and the dark modes, we are going to have a much simpler structure that this lattice is pairwise diagonalized. So when there are 15 photons in the B1 mode, it can only couple to the 14 photon in the B1 mode, and when the atom in the excited state. And the coupling strength is square root of 15. And the photon number in the dark mode does not change, right? So the second state is when the, so we redistribute the photon number in the B1 and B2 mode. We are going to find all these pairwise diagonalized states that the coupling strength only proportional to the photon number in the bright mode. Now, until you have this only 1 photon in the B1 mode and 14 photons in the dark mode, you have the last pair. And then if you have 0 photon in the B1 mode and all the photons in the dark mode, the atom cannot be excited. So there's one state left, and this state is just the soliton state we have introduced in the previous slides. And if you just calculate this distribution of the of this state in the A1 modes, you are going to find it satisfies all the criteria of the topological edge states. So this is the 1D SSH model. Of course, you can change the coupling strength between the cavities and the atom. For example, you introduce U1 and U2 to describe this difference. Then you are going to move this edge mode from in different positions of the Fock-state lattice. So this mode always locate at the boundary when these two cavities contribute nearly equally to the coupling to the atoms. So it can, you just tune the ratio between U1 and U2. You can move this state from the left side to the middle of the lattice and to the right, then to the right side. So this is one of the ways that you can transfer automatically the photon number from one cavity to the second cavity. And now we come to the two-dimensional Fock-state lattice, which means you have 3 cavities over here. And I have introduced that in this case, you are going to have a honeycomb structure. Here I have 20 photons, so this is much more like a honeycomb lattice. That you can already see that at the 3 vertices, you have all the photons in one of the cavities. And in middle of this edge, for example, you have the photon numbers equally distributed in the first and the second cavities. So immediately you find that the coupling strengths are going to be very ununiform, inhomogeneous in this lattice. For example, at one of the vertices, you're going to find, well, the coupling strength to the first cavity is the square root of 20, while the coupling strength to the other 2 cavities are just 1s. So this is a very inhomogeneous. While in the middle of the lattice, you are going to have relatively the same coupling strength in the 3 cavities. So this is a kind of strained graphene. It can be, if you strain a graphene on some substrate, you can tune the coupling strength as well. So we just look into the literature, how people study this kind of strained graphene. So graphene has a very special band structure. It has 6 Dirac cones, actually 2 equivalent Dirac cones in the Brillouin zone. And these Dirac cones touch at the K and K prime points. And if you have some strain on the graphene, then these Dirac points are going to move in the Brillouin zone. And if you strain it strong enough, then you are going to have 2 Dirac cones merge to 1, and then band gap open. And this is called the Lifshitz topological transition from a semi-metal to an insulator. So here the first question is, in this Fock-state lattices, we definitely have this kind of 2 phases. So one is the semi-metal, the other is the insulator. The question is, where is the insulator phase and where is the semi-metal phase? There's a criteria of the semi-metal phase that the coupling strength at one side to the 3 neighboring sides, if they can satisfy this condition, which means the strength of these 3 hopping coefficients can form a triangle, then you are going to be in the semi-metal phase. Otherwise, that is the insulator phase. So in this Fock-state lattices, after calculation, we found that, well, in the in-circle of this triangle boundary, you have the semi-metal phase. Otherwise, the other parts are in the insulator phase. So this is actually very interesting that you can have this like a very perfect division of these 2 phases. And people also have studied the effect of the strain when the graphene is on a very special substrate. The effect actually is equivalent to a effective magnetic field. So because when you strain a graphene, the Dirac cones move in the Brillouin zone. So the P is moving, have a new points that have the 2 cones touch. So that is effectively a gauge field. And after calculation, you find that, well, this kind of gauge field are going to lead to Landau quantizations. So the electrons near the K and K prime points are going to be in quantized Landau levels. And people have measured this kind of Landau levels and see that the scaling is proportional to the square root of n times the magnetic field. And the strain-induced Landau strain-induced effective magnetic field can be as large as 300 Tesla. So which is basically impossible to realize in real lattices. So here we come back to the 3-mode GC model to see whether we also have this kind of magnetic field and how large is the magnetic field. This is the next question. Actually, the calculation is very easy. We just follow the method we have used in the one-dimensional Fock-state lattices by combining these 3 cavity modes to one bright mode. then the atom is only coupled to the bright mode, and we have two dark modes left. Then we draw, just calculate the eigenenergy. That is very easy because you must have this square root of n quantized energy spectra, and the other degree of freedom is the difference between the photon numbers in the two dark modes. So we define a quantity which we call the chirality, which is corresponding to the spin chirality in the spin system. Actually, they basically follow the same physical rule. And this C can also be used to characterize the K and the K prime points of the Brillouin zone, actually. So when C is the smallest C, so here we have 20 photon numbers. So when C equal to -20, that corresponds to one valley of the Brillouin zone. And K prime, which is the maximum C, is corresponding to the other valley. So so K and K prime points are here. One interesting thing over here is that we immediately see the connection between the GC model and the Landau quantization of the electrons in graphene. So these two models actually cannot be further apart, that people have never considered that they are related. So here we have the GC model quantization, which follows the square root of n scaling. But if you look into the electrons graphene electrons in a magnetic field, you are going to find a similar scaling, which is also square root of n. And these two must be equal to each other because we have a string-induced magnetic field in the Fock-state lattices. We can use this formula to extract the value of the effective magnetic field in Fock-state lattices. So this is the same equation. And the only thing that we need to identify is the hopping coefficient T. The hopping coefficient is also easy to obtain because we have in the middle of the lattice where the string is relatively weak, that we have the hopping coefficient, that is the background hopping coefficient, which is G square root of n over 3, where the photon numbers in the three cavities are basically equal. And with this relation, we found that the magnetic length, which characterize the strength of the magnetic field, and the lattice constant, their ratio equals to n over 2, where n is the total photon number in this three-mode GC model. So now we have a chance to estimate how large is the pseudomagnetic field. If you want to observe the same dynamics in the Fock-state lattices in graphene, how large is the magnetic field you're going to have? So with n equal to 20, we found that the magnetic field is more than 3,000 Tesla. So an incredible number in real world. And if you have a smaller number, total excitation number, you are going to have even bigger magnetic field actually. And this magnetic field, after more careful calculation, we found that is position dependent. It's not a constant. So near the edge of the in circle, you're going to find that is it diverges. And we can also calculate the wave functions in the Landau levels, the quasi-Landau levels. For example, in the zeros Landau level, we found that is very similar to the wave functions in real magnetic field graphene of electrons in a graphene in a real magnetic field. And we can also study, some response of the excitations of the photons to make comparison with those condensed matter physics. So for example, we can prepare the states in one of the K point, and which in the Fock-state lattice is in the center of the lattice. And we can introduce effective electric field because the string already give you a magnetic field. Now, if you introduce effective electric field, which is just a linear potential in this lattice, and it's easy to introduce. Just introduce a detuning between the two modes, you are going to have this linear potential. Then what you are going to observe is that there's a Bloch oscillation within the zeroth Landau level, that the electrons travel from one key point to the key prime point and then come back. And then in the real space, you are going to find the wave packet moves perpendicular to the electric field, which is actually exactly the response, characteristic response of the Hall current, right? So if you have magnetic field perpendicular to the plane of this lattice, and then if you have electric field to the right, then you have this an upward Hall current. And then at the boundary, the wave function is reflected by the boundary between the semimetal and the insulator. Then it comes to the K prime valley, where the magnetic field have the opposite sign. So the wave function moves downward and then upward. So you are going to have this oscillation. And if you change the direction of the electric field, you're going to see that the motion of the wave packet always perpendicular to the electric field, which is natural for the Hall effect. And of course, you can construct other models in this artificial lattice structure. For example, the Holden model, you can introduce this term in the Hamiltonian, which carries the next neighbor hopping with a phase, such that you're going to find the band structure, the Landau quantized band structure becomes something like this. You have two bands, and then the zeroth Landau level becomes, have a finite tilt over here. So, which means actually, so originally they are localized states. Now they're going to have some chiral momentum. So if you prepare an initial state, for example, at this position, you're going to find this wave packet will move around the in circle in a certain direction determined by this tilt. And of course, with other parameters in this Holden model, you can actually construct the original Holden model with arbitrary phase, such that you can map out the original Holden model phase diagram by using the topological marker. Because this is a finite lattice, so you cannot use you cannot calculate the number of the band using the regular calculation of the topological number of the band structure. So but you can still, fix position in the lattice and calculate the local topological marker, which give you exactly the same result actually compared with because all these kind of edges or these local perturbations does not change the band structure, the topological nature of this lattice. So you can still obtain the phase diagram of the Holden model, original Holden model. So with the last few minutes, I would like to introduce the experimental realization of this model. So originally cavity QED used real cavities. For example, in the 80s, people use readable atoms and the real cavity of this. But it's really difficult to really couple the real cavities to the atom. So the model, the experimental platform we are using actually is thanks to the development of the Josephson physics, that people in the 80s already observed the quantum property of a Josephson junction. Then the managed to build a qubit of this and couple the qubit to the coplanar cavity resonator. And this has become a very hot area that people study the quantum computation. And in Zhejiang University, we can also manufacture the chips, and we have these different chips containing different number of qubits. And now we have like 20 qubits in a chip, and we can do some experiments on the topic I have just introduced. These are just some basic characteristics numbers of this chip. And recently we have did some experiment-like synthesis of the antisymmetric spin exchange interaction in the 5-qubit system, and did some quantum optics related experiments. And also we have synthesized the Zhejiang catastates, the 5-component Zhejiang catastates of up to 20 qubit. And for this experiment, we fabricated a sample like this. We have 3 resonators coupled to a central qubit, and the coupling strength between the qubit and the cavities are tunable such that we can move the topological edge states of the Su-Schriefer-Heeger model from one cavity to the other cavity, and the fidelity is like 80%. And for the valley Hall effect, we just need to first transport the SSH state to the middle of the lattice. Then we apply an effective magnetic field. Then the states we see that it will go perpendicular to the effective electric field we have applied, and to the other edge of the inner circle then comes back like what we have predicted. So at the end, I think the time is running out. Just at the summary, make a summary of this talk. So we have managed to study the topological phases of quantized light in 1 and 2 dimensions, and this lattice can be extended to higher dimensions. For example, to study the 4-dimensional quantum Hall effect. And the theoretical result has been published in National Science Review. People interested can download the paper also from the archive. So at the end, I would like to thank my collaborators. So Marlon Scully from Texas A&M. We have collaborations on the superradiance lattices, and Rinbao Liu for the inspiration many years ago. And we have atomic lattices, both in cold atoms and hot atoms, led by Jing Zhang and Junxiang Zhang, respectively. And in particular to my colleague Haohua Wang, who fabricated the sample to study these new topological phases of quantized light. And thank you.
Okay. Thank you, Da-Wei. That was an amazing talk. Do we have any questions from the audience? If you have any questions, please put them in the Q&A box or raise your hand. Okay, so in the meantime, can you, so I'm a theorist and I find all the experimental work deeply confusing and incredibly challenging. Could you maybe talk very briefly about what are the bottlenecks in experiments involving observing topological effects in light?
Well, thank you for the question. In the experiment, the bottleneck actually is the controllability. And so when we tuning, for example, in this topological edge state transport, when we change the coupling strength of the cavity between the cavity and the qubit, they always can at the same time change the resonance frequency of the cavity. So actually, it's very hard to make the tuning that you expect. There's always some side effect. We need to, at the same time, to compensate the side effect. And when the photon numbers goes to very high, for example, here we just have 4 photon numbers. If you goes to 10, there's another thing that is that will stop us, which is the non-linearity of the cavity. So the cavity basically they have very small non-linearities, like the n photon states is not exactly 10 h bar nu, but it's slightly different from there. And that will also bring some side effects that we don't want to have. So what we can see that is we need to develop new skills or new design to compensate all these the nonlinearity and the crosstalk between the control.
Mm-hmm. Okay, thank you. So if there are any more questions, we can all thank Da-Wei silently again. And
thank you everybody.
Yeah, so this is almost the end of the conference. I would just like to invite Min-Shu to give a few concluding remarks.
Yeah, thank you, Mária. So before I conclude and thank everyone, Professor Hiroshi Imai from University of Tokyo would like to make one announcement. So Hiroshi, I think you can share your screen now and you can turn your video on if you would like.
Thank you, Min-Shu, and thanks so much for program committee members and also local organizers and also student volunteers for AQIS year 2020 Sydney. So I hope you are now seeing AQIS, a plan for AQIS year 2021. I'm sorry. AQIS year 2021 Tokyo, and plan is we will have it in summer in 2021. But here are a lot of issues like this year. I'm sorry. Of course, we are now facing a severe situation concerning the COVID-19. And as for year 2021, there are issues as far as Tokyo is concerned that the Olympic Games Tokyo 2020 will be celebrated from July to August next year, 2021. So it has been extended, and they are planning to have real Olympic Games here in Tokyo. And this is also the case for the Paralympics Games Tokyo 2020. It will be celebrated from August 24th to September 5th next year, 2021. And of course, we have a big issue. Nobody knows what is the situation about COVID-19 in the next August or September in year 2021. But so current plan, we are happy to have AQIS 2021 in Tokyo, considering the Paralympics Games Tokyo 2020 will be celebrated from August 24th to September 5th and 2021. Candidate date is a week starting from September 6th, year 2021. So from the next day at the end of the Paralympic Games, we are planning to have AQIS, Asian Quantum Information Science Conference in Tokyo. Venue would be around University of Tokyo. The background image is our red gate of the University of Tokyo. And I hope it can be held in a physical conference, but it may be virtual or hybrid between virtual and physical. And we will do our best to welcome you all to Tokyo. It might be virtual again. So please check for further information at aqis-conf.org for further updates and so on. And so thank you so much for all the members who made AQIS 2020 so successfully like this. But we hope to see you at Tokyo next year, year 2020-21. So that's all. Thank you, Min-Shu. So I will stop my sharing.
Thank you, Professor Imai. Zhejiang, do you want to say a few things before I conclude and thank everyone? Can you hear me, Zhejiang? Okay, so we will see. So finally, I would like to thank everyone who have participated and contribute to AQIS 2020. AQIS has been a very enjoying conference. I started participating in AQIS since 2006. It has been like 14 years in a row. I enjoyed this conference very much. I hope you would enjoy this conference as well. Hopefully, it's too bad this year we cannot invite you all to Sydney to enjoy this conference, but hopefully next year we can all see each other in Tokyo, Japan. If Da-Wei Wang did not have anything to say, then I would just conclude this conference and thank you everyone. Thank you for joining. Okay. Thank you everyone.
I just want to add one thing.
Oh, okay. Da-Wei Wang is here.
Okay. Thank you very much. Your effort, Minshu and the program committee members, and this time we are missing one thing. There is a group photo. So, but hopefully next year we are going to have a group photo in Tokyo. See you.